Hello everyone, today we will learn about definition of sequences and some examples. Sequence: a function whose domain is the set n of natural numbers and range a set of real numbers is called a real sequence. A real sequence is denoted by S colon n to R, that is, S is a function from set of natural numbers n to R. It can also be denoted by F is a function from n to R, or small a is a function from n to R. Since the domain of a sequence is always n, a sequence is specified by the values Sn, where n is natural number. A sequence may be denoted as Sn, n belongs to n, or S1, S2, S3, Sn. The values S1, S2, S3 are called the first, second, third terms of the sequence. The mth and nth terms for m is not equal to n are treated as distinct even if Sm is equal to Sn. Thus, the terms of a sequence are arranged in a definite order as first, second, third terms, and the terms occurring at different positions are treated as distinct terms even they have the same value. Example 1. Let Sn is equal to minus 1 to the power n, n belongs to n. Here for n is equal to 1, S1 is equal to minus 1 to the power 1, this is equal to minus 1. For n is equal to 2, S2 is equal to minus 1 raised to the power 2, this is equal to 1. So, S2 is equal to 1. Similarly, for n is equal to 3, S3 is equal to minus 1, S4 is equal to 1, S5 is equal to minus 1, . So, only two distinct elements are minus 1 and 1. Example 2. Let Sn is equal to 1 by n, where n belongs to n. Therefore, S1 is equal to 1, S2 is equal to half, S3 is equal to 1/3, S4 is equal to 1 by 4, S5 is equal to 1 by 5. In this case, all the elements are distinct. Example 3. Let Sn is equal to minus 1 plus minus 1 raised to the power n, where n belongs to n. In this case, for n is equal to 1, S1 is equal to 1 plus of minus 1 to the power 1, this is equal to 1 minus 1, this is 0. For n is equal to 2, S2 is equal to 1 plus minus 1 to the power minus 2, this is equal to 1 plus 1, this is equal to 2. Similarly, S3 is equal to 4, S3 is equal to 0, S4 is equal to 2, S5 is equal to 0. So, only two distinct elements are 0 and 2. Example 4. Let Sn is equal to minus 1 to the power n, where n is natural number. For n is equal to 1, S1 is equal to 1, S2 is equal to 1, S3 is equal to 1, S4 is equal to 1. Therefore, only one element 1. So, range of this sequence is 1. The range or the range set is the set consisting of all distinct elements of a sequence without repetition and without regard to the position of a term. Thus, the range may be a finite or an infinite set without ever being the null set. Bounds of a sequence. Bounded above sequences. A sequence Sn is said to be bounded above if there exists a real number capital M such that Sn is less than or equal to M for all n belongs to n. Bounded below sequences. A sequence Sn is said to be bounded below if there exists a real number small m such that Sn is greater than or equal to m for all n belongs to n. Bounded sequences. A sequence is said to be bounded when it is both bounded above and bounded below. Convergence of a sequences. Convergence of sequences. A sequence Sn is said to converge to a real number L if for each epsilon positive there exists a positive integer m depending on epsilon such that modulus Sn minus L is less than epsilon for all n greater than or equal to m. In other words, the terms approach the value L or tend to L as n becomes larger and larger, or limit and tends to infinite Sn is equal to L. Some theorems. Theorem 1. Every convergent sequence is bounded. Proof. Let a sequence Sn converge to the limit L. So, by definition, let epsilon be positive given a number. So, there exists a positive integer m, small m, such that modulus Sn minus L less than epsilon, or distance between Sn minus L is less than epsilon for all n is greater than or equal to m. This if and only if L minus epsilon less than Sn less than L plus epsilon for all n is greater than or equal to m. Let a small g is equal to minimum of L minus epsilon S1, S2, Sm minus 1, and capital G is equal to maximum of L plus epsilon S1, S2, Sm minus 1. Therefore, we have G is less than or equal to Sn less than or equal to G for all n. Hence, Sn is a bounded sequence. The converse of the above theorem is not true. That is, every bounded sequence need not to converge. For example, the sequence Sn is equal to minus 1 to the power n, n belongs to n. Its range set is 1 and minus 1, which is bounded, but it is not convergent. Theorem 2. A sequence cannot converge to more than one limit. That is, limit of a sequence is unique. Proof. Let, if possible, a sequence Sn converge to two real numbers L and L dash, where L is not equal to L dash. Let us consider epsilon is equal to 1/3 modulus L minus L dash, which is greater than 0. Since the sequence Sn converges to L and L dash, therefore there exist positive integers small m1 and small m2 such that modulus Sn minus L less than epsilon for all n greater than or equal to m1 and modulus Sn minus L dash less than epsilon for all n is greater than or equal to m2. Now from 1 and 2, for n greater than or equal to maximum of m1 and m2, modulus L minus L dash is equal to modulus of L minus Sn plus Sn minus L dash, which is less than or equal to modulus of L minus Sn plus modulus of Sn minus L dash, which is less than epsilon plus epsilon is equal to twice epsilon, which implies that L minus L dash is less than 2/3 modulus L minus L dash, which is not possible because modulus L minus L dash cannot be less than 2/3 of modulus L minus L dash. Hence, the sequence cannot converge to two limit points. Therefore, neighborhood of a point. A set n contained in R is called the neighborhood of a point A if there exists an open interval I containing A and contained in N, that is A belongs to I contained in A. Limit point of a sequence. A real number xi is said to be a limit point of a sequence Sn if every neighborhood of xi contains an infinite number of members of the sequence. Thus, xi is a limit point of a sequence if given any positive number epsilon, however small. Sn belongs to xi minus epsilon, xi plus epsilon for an infinite number of values of n, that is modulus Sn minus L less than epsilon for infinitely many values of n. A limit point is also called a cluster point or a point of condensation. A number xi is not a limit point of the sequence Sn if there exists a number epsilon positive such that Sn belongs to xi minus epsilon, xi plus epsilon for at the most a finite number of values of n. A limit point of the range set of a sequence is also a limit point of the sequence, but converse may not always be true. The constant sequence Sn is equal to 1 for all n belongs to n has the only limit point 1. The range set 1. The range is 1 and has no limit point. The sequence Sn is equal to 1 by n, n belongs to n has 0 as a limit point, which is as well a limit point of the range 1, half, 1/3. 0 and 2 are the only limit points of the sequence Sn is equal to 1 plus of minus 1 raised to the power n, n belongs to n. The range set 0, 2 has no limit points. 1 and minus 1 are the limit points of the sequence Sn is equal to minus 1 raised to the power n belongs to n. The range set 1 minus 1 has no limit point. Bolzano-Weierstrass theorem for sequence. Every bounded sequence has a limit point. Upper and lower limits. The set of limit points of a bounded sequence has the greatest and the least members. The greatest and the smallest of the limit points of a bounded sequence are respectively called the upper limit and the lower limit. The sequence Sn is equal to minus 1 raised to the power n belongs to n, is bounded for minus 1 less than or equal to Sn less than or equal to 1 for all n belongs to n. Also minus 1 and 1 are the only limit points. Therefore, upper limit is equal to 1 and lower limit is equal to minus 1. The sequence Sn is equal to 1 plus of minus 1 raised to the power n for all n belongs to n is bounded for 0 less than or equal to Sn less than or equal to 2 for all n belongs to n. 0 and 2 are the only limit points. Therefore, upper limit is equal to 2 and lower limit is equal to 0. The sequence Sn is equal to n square for all n belongs to n is 1, 4, 9, 16, 25. For n is equal to 1, S1 is equal to 1 square, this is 1. For n is equal to 2, S2 is equal to 2 square is equal to 4. And similarly 9, 16, 25, 36. The sequence is bounded below but not above. The lower value is 1, so it is bounded below but it has no upper limit. There is no real limit point. Limit inferior and superior. Definition. Let an be a sequence of real numbers, not necessarily bounded. We define limit n tends to infinity, infimum of an is equal to supremum n, infimum of an, n plus 1, an plus 2 up to infinity, which is also denoted by limit under bar n tends to infinity an or limit under bar an. And limit n tends to limit n tends to infinity supremum of an is equal to infimum of n supremum of an plus 1, an plus 2 up to infinity is equal to limit bar an tends to infinity is equal to limit bar equal to an as the limit inferior and limit superior respectively of the sequence an. We shall use the following notations for the sequence an for all n belongs to n. A under bar an is equal to infimum of an plus 1, n plus 2 dot and a bar n is equal to supremum of an plus 1, an plus 2 up to infinity. Therefore, we have limit under bar an is equal to supremum of, therefore, limit under bar an from this limit under bar an is equal to supremum of n a under bar n and limit superior n is equal to infimum of n a bar n. If an is any sequence, then infimum of an is less than or equal to limit inferior is less than or equal to limit superior less than or equal to supremum of an. If an is any sequence, then limit inferior of minus an is equal to minus of limit superior an, and limit superior of minus an is equal to minus of limit inferior an. Limit inferior and superior examples. If an is equal to minus 1 raised to the power n belongs to n, then a under bar n is equal to infimum of an plus 1 n plus 2 is equal to infimum of minus 1, because if n is equal to 1, then a1 is equal to minus 1, n for n is equal to n, this is minus 1 to the power n is equal to n plus 1, this is minus 1 to the power n plus 1, and the only terms repeats are minus 1 and 1. So, minus a under bar n is equal to infimum of minus 1, 1, minus 1, and this is equal to minus 1, and a bar n or an bar is equal to supremum of minus 1, 1, minus 1 is equal to 1 for all n belongs to n. Therefore, limit inferior an is equal to supremum of n a under bar n is equal to minus 1, and limit superior n is equal to infimum of n a n bar is equal to 1. If second example, if an is equal to 1 plus minus 1 raised to the power n belongs to n, then a under bar n is equal to infimum 0, 2, 0, 2 is equal to 0, and a bar n is equal to supremum 0, 2, 0, 2 is equal to 0 for all n belongs to n. Therefore, limit inferior n is equal to supremum of n a bar n is equal to 0, and limit inferior an is equal to supremum n a under bar n is equal to 0, and limit superior n is equal to infimum of n a bar n is equal to 2. Example 3. If n is equal to minus 1 raised to the power n into n belongs to n, then limit inferior n is equal to supremum of n infimum of minus 1 raised to the power n minus 1 raised to the power n plus 1 into n plus 1. This is equal to supremum of minus infinite up is equal to minus infinity. And similarly, limit superior n is equal to plus infinity. Thank you very much for watching. Please don't forget to subscribe my channel. Please like, share and comment. Please press the bell icon to get notifications.